after the Genève Lake in Canton Valais, it's used in CERN. In Switzerland, they are not used for monitoring of railways because the railways network is so dense that the crosstalk between different sensors is pretty high. So it just doesn't make any sense. But in Germany, UK, it's really a common technology. And another technology is FMCW LiDAR. How it works? We detect distance not with time of light, which goes to a target and back. We detect it with frequency. So we have our frequency modulated light. It goes to a target, it reflects back, and we detect it with our local oscillator using heterodyne technique. And then we don't need a lot of photons coming back. So it's like pretty sensitive technology. And this is extremely accurate because we are measuring frequency. And like the best thing which you can measure in physics, in photonics, and engineering is frequency of something. And then we just detect distance with the frequency. But then we need pretty good laser for this, and we need linear chirp. And speaking about linear chirp, let's take a look at this plot. I will make laser pointer here. So let's assume that we have linearly chirped laser light going to our target, and it can be ideally chirped. So this is like ideally linear line, or it can be with some deviations, non-linear chirp with this red light, with the red line. And then your bit node, which you detect on your side after heterodyne with local oscillator, depends on this chirp. It depends on the noise of the laser and linearity of chirp. And the red line is your bit node in case of non-linear signal. And ideally perfect linear signal will give you delta function, but it never happens, first of all, because we have laser noise. And our exercise will be pretty straightforward. We will see how this bit node looks like for different parameters. So for example, we have a car in 250 meters, light goes to a car, goes back. We can put different sweep rate of this light, and we can see different level of non-linearities of the signal and different noise of laser. And you will see that just with DFB laser diode, it's pretty hard to make a good FMCW LiDAR. But if we're talking about long-range LiDAR, for example, for again railways, or for example for detection of planes at the airports, we need pretty low noise laser. And our exercise will be devoted to this. And so what we are trying to do with COMS, so with just photonic integrated lasers, we are trying to bring the best of two worlds. First of all, the best of the world of bulky legacy laser systems, for example, optical laser, fiber lasers, coherent lasers, so this like big tabletop laser systems which give you ultimate performance, but then you can't really make any real application with this system. And another thing is lasers based on silicon photonics, for example, coherent transceivers, but they are not as high performing as we need, for example, for this application, which I mentioned, fiber sensing and FMCW LiDAR. And we are doing everything on a chip, designing photonic integrated circuits. And then everything can go into a small package. As I said, into standard butterfly packages, where inside we have laser diodes, active elements, passive elements, some actuators, stress optic, thermal optic, electro optic, and output fiber. And then this laser can be pretty good. Let's really briefly cover different types of lasers. So I will be pretty quick. And if you have any questions, like, feel free to interrupt me right now, because this presentation is like 30 minutes. We can do it quicker, and it makes sense if you ask your questions like now on spot. So how to integrate laser on a chip? We have different types of active materials. They could be SOA, semiconductor optical amplifier. So this is just like a piece of semiconductor, indium phosphide, for example, with angled waveguide in, angled waveguide out, and it just works as an amplifier. Also, there is reflective semiconductor optical amplifier. This guy, we have a high reflection here facet, so all light which goes here just like reflected back, and low refractive facet here, and then we just like butt couple it, for example, with a loop or grating on a chip, and it works as a laser. This guy is called RSOA or gain chip. Also, there are just like a piece of semiconductor with two high reflective mirrors here, 90% here, and something like 5–10% here. And this guy is called Fabry-Perot laser diode. Usually it has high output power, so they're used for fiber amplifiers, for medical application. The power can go to half a watt and even 1 watt of optical power. And the spectrum is multimode. So different lines, different frequencies correspond to different longitudinal frequencies, modes inside this cavity. Then we can put some grating on this cavity, and it will go into single frequency region, but it will have some mode hops when we tune it. And this guy is called distributed Bragg reflector laser. If we put this grating on the whole chip, this guy is called distributed feedback laser, DFB laser. So they are just like working horse of right now photonics. They're used in many coherent applications, but we clearly see that many photonic sensing systems are limited by this guy. And there are like many other different types of lasers. For example, wide emitter. It's like Fabry-Perot, but inside we have many special modes, because the emitter is usually 100 micron width, but the power of this guy can go to several watts, 10 watts of power. If there is a company from the States, it's making the stack of 3 emitters vertically, like wide emitters, the power goes in pulse region to 90 watts. And this is right now the laser which enables this famous FMCW LiDAR for self-driving cars. It's just like a very bright flash, and the light goes to targets, you get it back, and you see the 3D image of your thing. Also, there is lasers with vertical cavity VCSEL. They are pretty used in telecom because you can modulate them pretty fast. The cavity is really short, and the modulation time is really fast. Quantum cascade lasers, interband cascade lasers, and like we have all these different types of lasers. And the question is how we integrate all of this with passive devices, what is called heterogeneous integration. And speaking about this like integration, there are like different things. First of all, we can take just piece of semiconductor and butt couple, do hybrid integration with passive silicon nitride. It's called hybrid integration. If you do it in like more sophisticated manner, it could be called flip chip integration. So you take your chip and you just like do butt coupling on wafer level. So this is basically the same hybrid integration, butt coupling, but on wafer level. In this case, it's called flip chip. And this is the way how right now optical transceivers are built. Another promising technology is microtransfer printing. When you can do this flip chip assembly on multi-chip level, on wafer level, on multi-chip. This is promising technology. The performance isn't so great because it's like low power right now, but you guys know everything about this. Yes, our colleagues from UGent are working on this, so Bart Birkin is like the world expert in this thing. And there is die to wafer bonding or heterogeneous integration. So basically we have our passive lithium niobate, silicon nitride passive wafer, and we bond indium phosphide wafer, for example, on top of it. It was speaking about C-band. and then we process indium phosphide. It's called heterogeneous integration. Personally, I believe that this is the future, and right now there are like several foundries in the world. They offer it as commercial service. So basically, you can just order this material stack with all kinds of elements. Performance isn't amazing, but this performance is robust. So basically, this is foundry level process right now available from several foundries in the States. Speaking about history, what we are trying to do, we are trying to move from just like DFB laser diode, monolithic semiconductor lasers, to something sophisticated. For example, these Illinois lasers or lasers integrated with piezo actuators, which can give you narrow line widths and pretty fast actuation bandwidths, broadband actuation. This is important for coherent sensing. And speaking about our recent results, we plotted like the state of the art of photonic chip-based lasers, and there are lasers which can be low noise, ultra low noise, which can be frequency agile, for example, Illinois lasers, but also we can combine both of them, and that's what we are doing in K-Lab. So we have a laser which has line width of several hertz, and the flat modulation bandwidth is 400 kilohertz. This is better than any bulk laser can provide you in this form factor. For example, fiber laser cannot be actuated so fast. And I will really briefly cover several topics how we can build the laser. So here we like in Lausanne the approach called self-injection locking. So we have DFB laser diode, and then we have high Q optical cavity, and it allows us to make a pretty nice laser. Also, you can be inspired by DFB approach and DBR approach, and you have a piece of semiconductor, an amplifier, and then you have reflecting grating. And in this case, you have extended distributed Bragg reflector laser, which can be pretty good and in reality better than just DFB and DBR laser diodes. Or you can do vernier lasers. It could be dual ring lasers, it could be dual grating laser, but you need two frequency selective elements. They have their modes, and then you just like align this vernier filter and you have single frequency lasing. So this is the photograph of one of these dual ring vernier devices. So here we have two rings, so we are using only one pair of them. And speaking about physics, please free to consult with these two publications, one from Eugen, another from John Powers. They cover like the physics of these devices pretty nice. In our case, we try to integrate them with piezo actuators. So super briefly, how it works. We have our passive silicon nitride, and we have to change its frequency. We can change it with thermorefractive effect, just with micro heater, heating it, changing refractive index just with temperature. Or we can apply stress. Right now, we are doing it with two different materials, aluminum nitride and PZT, two different piezoelectrics. They're a bit different, but they does the same job. They apply some stress to waveguide, and the refractive index of this waveguide changes. And it turns out that this approach is faster and lower power consumption than with micro heater. You cannot tune a lot pretty far, but in reality, if you need like some fast tuning, for example, for locking your laser to another cavity, or just to scan across some feature, then this approach can be pretty nicely used. In our case, we had micro heater for broadband tuning, and this piezo actuators for fast tuning, for locking it, or for making this laser sweeping with high speed.
Like usually, like
yeah. So first of all, it's not a big issue for industry that we have to apply high voltage. It's not CMOS compatible, of course, so you don't have like on chip. But in reality, you can develop pretty small just electronic circuit which gives you high voltage with high speed. And this material PZT can be actuated with 10 volts. So in this case, it goes to low power. And right now we're working on different materials to move it to like several volts to like CMOS level. So this is promising, let's say so.
And also how fast does it need to be able to look at what's the speed that you
to lock
two lasers together, for example?
Yep, this is very good question. And in reality, the bandwidth of locking is defined by your setup. So you have cables everywhere, and this delay in all cables defines the bandwidth of your locking. And if you optimize your system, for example, you have direct bonding of your laser to electronics, then it goes to megahertz range. So like if you do it just like in the lab, most probably it will be 50 hertz, like 100 kilohertz range. But if you need to push it to the maximum, it easily goes to several megahertz. And in this case, you cannot do it with micro heaters. You need something really fast, electro-optics or this stress optics. And speaking about electro-optics, we tried another approach which can be as robust as just the laser diode. And we tried to integrate just like reflective semiconductor optical amplifier with a grating on LNY. We just apply some voltage, this grating changes refractive index, and we control the laser frequency. I have like many slides to explain how it works, but in reality, it works pretty fast and pretty good. We can change the laser frequency in the range of 10 gigahertz with the frequency. I think it's here in the range of here one megahertz, but it was limited by our high voltage amplifier. If we're talking about smaller chirp range, how far we tune, so for example, several hundreds of megahertz, we can do it in the bandwidth of 100 megahertz. And it becomes limited by our probes. So basically how we apply this voltage. And this publication, which is covered here, it appeared just several weeks ago from University of Rochester. They have modulation bandwidths up to 10 gigahertz. So if you do it properly, this is extremely fast laser. So basically you integrate your laser with electro-optic modulator in one package. Yeah, this laser can be really, really fast. So here, this is like logo of EPFL, and the here time scale is microseconds. So this is 5 microseconds, this letter E. So usually people are, how the people do it? They take pretty good laser with this phase noise, which is low noise laser with line width 3 kilohertz. And they add one more element, for example, electro-optic, external fiber-coupled electro-optic modulator or acoustic frequency shifter. And then they have this performance. In our case, with integrated photonics, it becomes possible just inside one butterfly, standard butterfly laser package. And also we can make something extremely low noise using self-injection locking. I can explain you how it works if somebody interested. Maybe we can cover it during our coffee break. But in reality, this is like the best right now, the best approach to make compact low noise laser. So this is the phase noise of different lasers. Feel free to ask me what is phase noise. 30K fiber laser is this red line. In case of self-injection locking, we are looking at lasers which has this like dark blue, light blue, and these purple lines. So these guys are self-injection locking. So basically in really compact package, so this is like 10 cubic millimeters, something like that. No, that's definitely not true. Like 100 cubic millimeters. We have the phase noise, which is even lower than fiber laser, which is this big. And then it becomes really enabling technology for coherent sensing. This fiber sensing application, long range LiDAR. As I mentioned, long range LiDAR, you have to track objects in kilometers from you. You cannot make it with regular laser. You need something really low noise. And this laser in standard butterfly package can be actuated pretty fast with really nice nonlinearity. Here you can see 0.08%. And from the exercise, you will see what noise it will give you. And we can modulate it pretty far, up to 2 gigahertz. And historically, it was like opposite. First, we demonstrated Soliton self-injection locking, and then we moved to just like laser development. But right now, who cares about this history? Let's put the story this way. So we can develop pretty nice lasers on a chip using all these approaches. And let's ask question ourselves, can we make these devices with Soliton MicrocomS inside one package? And yes, we demonstrated this for the first time. It was the biggest challenge. It was demonstrated by EPFL and Michel Lipson and Alexander Gaeta in the States. So we took just Fabry-Perot laser diode, pretty nice ring with nice Q factors, 100 gigahertz FSR, and we just like immediately observed comps. Immediately, it means it took 1 year of non-stop experiments. So if somebody is trying one experiment for 3 months and it's not working, it doesn't mean anything. So big discoveries are done like within like years. So we observed 100 gigahertz comp, and then we observed 1 terahertz comp. Why this is cool? Because you immediately can use this device for telecom applications. So basically you have from 1 laser diode and 1 chip multiple comp lines. This is good for telecom. You can use it for broadband spectroscopy. You don't need your widely swept laser, and basically you are limited by, let's say, 10 terahertz or 100 nanometers with sweep of your laser. Using these terahertz comps, you can go even to octave spanning comps. And right now there are publications where they demonstrated from the same fully integrated approach, broadband comp. So you can make F2F logging of this comp, you can make some metrology, or you can make spectroscopy. You take 2 these comps and you observe, you do down conversion of this optical spectrum to the radio frequencies. And then you see your absorption spectroscopy on your electrical signal analyzer. Then it goes into just like regular butterfly packages. We published it with Caltech, with Kerry Vahala. So we demonstrate turnkey Soliton MicroCom. So basically when everything is packaged, you just like press 1 button and it gives you the comp. It's here. We understood all physics about this thing. This is 30 gigahertz comp, and the phase noise of this guy can be lower than just expensive microwave signal generator. So we figured out how to do investigation of these comps. So we developed new technique, analysis of spectrograms to observe different Soliton states. And in the end, we moved to heterogeneous integration, again with John Bowers. So we provided them with our wafers, just with passive silicon nitride. They performed bonding with indium phosphide, processed it, and in the end, this guy was working as like heterogeneously integrated Soliton MicroComp. and it was done in 2021, right? Already 3 years ago. And right now, this technology is pretty matured and commercially available from several foundries. Speaking about application of these comps, this guy can be used for multi-channel LiDAR. So basically, the main limitation for LiDAR is the speed, because your light is pretty slow in reality. So your chirp light should go to one pixel, be reflected back. You should measure this frequency, and then you move your light to another pixel. And in reality, this system is extremely slow. One of the approaches is to use just like wavelengths multiplexing. You have like different light wavelengths for different pixels, and this approach is called massively parallel LiDAR. And we tried to use this fully integrated comp for this LiDAR experiment. We don't have the data of LiDAR experiment, but now we can, in this package, chirp all these comp lines simultaneously, so they can go into different special channels. And in this case, there is no need to go from channel to channel. You just go one line. So you do one scan, not like 2D scanning. You do 1D scanning of this thing. And yep, some explanation how it works, how we do this chirp. We have solid and microcomp, and then different comp lines go to different points just because of the special multiplexing. And I think we can, if you have any questions, let's discuss them. We can move to our exercise, where we will try to simulate the performance of this system, FMCW, and we'll understand what are requirements for the line width and for the chirp linearity. Questions? Not really. So like, let's move to the exercise. This is like pretty straightforward. No console files today. It's just like Python notebook. Have you downloaded it? Yep. Let's then. I know what I don't know what is the best approach, because I cannot really see what is written here. Is it better on Zoom?
No, they're not connected. They're not connected.
Are you connected to Zoom or not?
No.
Okay. So this is the only thing which you can see. This one, yeah? Okay.
There is Zoom in the browser.
Yes, but yeah, are you connected to Zoom?
But like Zoom is really good, so
Does it help?
it's already.
No. Yep. Let's start with regular board. Like this. So the idea of exercise is the following. So we have our laser frequency, and we have our time. Laser frequency goes forth and back, and this is on the noise. This is frequency of light. So we are chirping it with some frequency. We have two issues with all lasers. So they are usually somehow noisy. Some of them are low noise, some are not so low noise. And this chirp is not linear. In ideal case, FMCW LiDAR works with a very simple approach. So the light was reflected back from your target, and you have your shifted light which comes back. So you have your local oscillator, what you stored on a chip, and this is what was reflected. So basically, if you multiply two signals with tetradyne detection, you will see like this. You will see this thing. Here we have like some difference of frequencies of light, and then they go to zero. Here we have zero frequency, and then here it starts to increase, and then in this region this is constant. In reality, why people like this stable LiDAR? Because it gives you also Doppler shift. So this line will be shifted up or down just because of the Doppler shift from your target. And in reality, you will have something like this. And by difference of these two frequencies, you will know the radial speed of your target. But let's forget about this. In our case, this is static target, and signal will be like this. So that's what we see on our electrical signal spectrum analyzer. So this thing, so it's already spectrum of this guy. We are working with just like time series, so we have to make some FFTs to get this picture, but it gives you an idea. So first of all, you have these turning points, and usually people just like throw them off. Nobody needs that. So you just apply some filter here. Always when you do FFT, you do zero padding. Also, you are using some filters to avoid your analytical error. So we have this guy, and then we have this frequency, and then we in real systems we do averaging on several periods, like 10, 100. If you take only one, this definitely will be a noisy LiDAR. And you just know this frequency. What affects it? In reality, your light is really noisy here. Your laser is noisy. And then this line also will be noisy. And second thing, what defines the linearity of this chirp is called flat actuation bandwidth of your laser. So how precisely you can tune your laser. For example, if you do it with microheater, the bandwidth of microheater is only 10, 50 kilohertz. It's definitely not enough, because usually this frequency is 10 kilohertz sweep rate. And to have this ideally linear chirp, you have to make very simple exercise. You have this time series, you do FFT, and you see how far the spectrum goes. And in reality, when it goes to 150 of these sweep rates, or 150 kilohertz, that's ideal bandwidth which you need to have this ideal linear chip. This is like pretty broad thing. This is 1.5 megahertz. No microheater can give you 1.5 megahertz actuation bandwidth. But with electro-optics or stress optics, it becomes feasible. All people are doing some linearization, but with linearization, you have some drifts in the system, and that's like what people are using right now in industry, but they all confirm that it would be better to move some better approaches. And this like if your signal is not linear, you have some deviations, some stuff like this. It can be like any shape, and this thing will affect your bit node here. So in reality, it will be pretty weird. And I showed in my presentation how it was. This guy can be pretty non-linear, and what we call linearity is called, so this difference divided by RMS of this guy divided by the frequency. And in reality, if your LiDAR laser has non-linearity not as good as 0.01%, then you will have pretty noisy signal here, and you will see it from the bit node. So from the exercise, everything is straightforward. The only not straightforward thing will be this guy. How we define this non-linearity chip. And in our case, we do pretty simple assumption. So we have our chip, and we will add some noise, but also we will add everywhere, just like parabolic function, quadratic function. Let's say that our laser is tuned like this, not with like linear chip, with just like some parabolic deviation. And then we have two shifted parabolas like this, and we have just to take integral of this guy, and there will be one formula where we just recalculate the level of this non-linearity, because you have to take average between them. So there will be just like one formula where we try to calculate this integral and recalculate it into just RMS error, which is this guy, and it will be just like square root of 30. So it goes like from the pretty simple equation where we're doing integral of this guy minus tau this guy, and it goes from to the period. Yeah, and we have to take square root of this. Yeah, this guy. So basically, when we integrate this and we try to make simple analytical formula, it will give us square root of 30. Any questions? And this screen, yeah, it looks here. So we have two different approaches. So we can just rewrite the script, or we can just take a look at all lines. What do you prefer? Okay, let's take a look. Let's import some stuff. We will need our Lorentzian noise. Laser has two different types of noises: Gaussian noise and Lorentzian noise. And the Cauchy function from math is just Lorentzian function from physics. What we do here? Here we just define the nonlinearity of our signal. In reality, chirp range and relative non-linearities. So we have this guy and we have this deviation. And we just calculate the deviation of this thing. We take RMS of this guy and divide it by this range. which is called frequency excursion. And this thing gives you, so this is C is chirp range, your frequency excursion, and this is this in percents, for example, 0.1%. And then we have chirp frequency, we create our time vector, and then we make ideal chirp. So we just like create ideal laser frequency chirping. We are working, in principle, we have to work at laser frequencies 2 by 10 to the 14, so laser frequency. But if we do this, we will have so many numerical errors in our calculations that it will give you a lot of just like errors in your result. So immediately we scale down from laser frequency to radio frequencies. We just like get rid of sine functions at laser frequency everywhere. So, and this is our chirped laser frequency. So in reality, it should be multiplied by exponential function and sine function with laser frequency, but we just get rid of this. And then we just add this parabolic nonlinearity. So why it looks like so weird, as I explained, it goes just from this integral. So here we recalculate our RMS nonlinearity, just like so basically this value into a real parabolic deviation of our function. And this is important that it should be 0 here, and it should be 0 here. Otherwise, it's not clear where is your turning point of your signal. Then we have this nonlinearity. We created this function, and then we just add this. We make a time trace of this nonlinearity, and here we just like create some variables, and we go into averaging. So here we just define how many periods we will take. Right now this is 1, but in reality, if you just like put several periods here, they will be averaged in this line. Here we create the frequency noise of our laser using just like Lorentzian line width, and just like sum everything. Ideal chirp, noise plus nonlinearity, and this is time series. We got rid of sine function, and that's why we have to work with phases. And we just calculate the frequency shift, deviation of the frequency of our deviation of phase, our laser. It's done like pretty simple. We just like do cumulative sum of our instantaneous frequencies. From this phase, we are getting to signals already down converted to the radio frequency, and add some zero padding. This thing we used for just for debugging to see the real frequencies of the laser, and we just like multiply them with 2-bit node. We do some windows just to make our FFT smoother, and we do FFT of our signal just of difference of these two guys. FFT is double-sided, so here we just go to one-sided FFT to detect the peak of our bit node, and average if we are doing averaging, and just return all the stuff. After that, let's use this function. We need sampling rate, so just like the distance of points in our time series. Chirp range, how far we tune our laser. Chirp frequency, how fast we tune our laser. Averaging one is one, so we're just looking at one bit node. And the delay line, usually when we benchmark our system, when we study our system, we are not doing real 500-meter light experiments because it depends on the weather condition. We need a mirror somewhere. And we are just using fibers. So we have a fiber spool with 500 meters. And here we just like take into account the refractive index of our fiber. Line width and linearity we will sweep. Average is 1. And here we just put different values of linearity in percents, not in percents. No, not percents. Just like values of linearity and line width. This is 1 kilohertz, 10 kilohertz, 100 kilohertz, the range and line width of our laser, white noise of our laser. And let's just like sweep across different line widths and linearities and just apply our function to our parameters. And then we just like plot all of them. So here we calculated all of them, and here we just like generate plots centered next to the central frequency. So we don't know where is this like bit node will be, so we have to define it and just plot them. And here we just like make our plot fancy. So let's try if it works. If you put more like higher sampling time and more parameters, it really can take a while to calculate it because of FFT. But for these parameters, it works pretty fast. So what we can see here, here we can see bit node for different line widths and different non-linearities of our laser. So how big was that additional parabolic function? If we take like the worst case, line width 100 kilohertz and linearity 1%, which corresponds to low-cost DFB laser diode, for example, from Torlabs. This is your bit node. So basically, if this is like 50 megahertz and this is at least 5 megahertz, so this is 10% 10% deviation. So basically, we don't know what is our target. We know it only with like 10% accuracy. And the problem is that signal to noise ratio is extremely small. So this guy is not useful for this type of LiDAR. You can change parameters here. You can play with it. And you can see that if we are going to short range LiDAR, for example, in space LiDAR, for example, for warehouses, for just like big stores where robots should like put like different shelves and they need to range it within like 10 meters. In this case, this LiDAR can be good. So you can play with this delay line here and you will see that these bit nodes will become pretty good. But speaking about self-driving cars, where we need hundreds of meters, this LiDAR is useless completely. And if we take better lasers, but we keep the linearity the same, 1%, you see, it doesn't really help. So we definitely need better linearity. We are improving our laser and going to linearity 0.1%. And this is level of our linearity of our lasers without any linearization. And our lasers are extremely low noise, below 1 kilohertz. And the bit note is pretty good. It's not excellent, but it's kind of useful. And we're getting excellent results only starting from line width 10 kilohertz and nonlinearity 0.01% of this like additional nonlinearity caused by the parabolic function. And in reality, this thing is used right now in the industry after linearization. So people have just DFB laser diode, extremely good DFBs with line width 30 kilohertz, and they do pre-distortion and active linearization of LiDARs using on-chip delay lines, on-chip spirals, and they linearize it to this level and use this just like intrinsic line width of good DFB laser diode, and they have this LiDAR. In principle, if you want to get rid of this linearization, which can be extremely expensive, with these photonic integrated lasers, LNY or self-injection lock lasers, we can jump to this thing. So signal to noise ratio is not definitely as good as we have here, but we got rid of this linearization unit, which costs at least 50% of the price. And here again, it goes to the system engineering and trade-offs in your system. So any questions here?
Can you repeat how on chip, how do you do the linearization?
So how we do linearization? Usually it's done in this way. This is like your laser unit, and you split it into two passes. So here it goes to your target. How to, we need a lens. Then this is one mirror. This is another mirror, and then it goes to your target. And here we have a car. And at the same time, you have to linearize it. How we're doing it in our case, we take some portion of light and we split it again. And here we have some delay line. In our case, we are using 14 meters of optical fibers, this spool of fiber. And this guy is just goes without anything. And then we have balanced photodetector. And here we have our oscilloscope. So in this case, this part of the system is stable, and you can do active monitoring of the laser chip here, just by doing heterodyne detection of this light and this light. Basically, this is the same photonic frequency modulated continuous wave LiDAR, but it's not real target. We have a fixed delay line fiber source. And this is just piece of fiber. And you just like with this oscilloscope detect your laser frequency actively, and you do compensation of laser chirp inside your laser using this ROC. If you Google for the company called Silk, yeah, that's the name. They are part of this company. They used to be founders from Mellanox. Silk. and they have a lot of photos, images of their LiDAR unit on the web, and you will see inside photonic chip with some spiral structure. And this guy is just like photonic chip-based delay line, several meters, maybe 10 meters of delay line on the chip just for this purpose. So they have inside DFB laser diode, then they have this delay line for linearization, and then they use linearized light for real measurements. Any other questions? Let's do exercise. So let's run it and change parameters to, let's see how it works. Something real, let's say. So we need line width. Could be 1 kilohertz, 30 kilohertz, and 1 megahertz. And the linearity should be 0.01%, 0.1%, and 0.1%. It stays the same, and the delay line will be 10 meters. Yeah, you have to change like several lines and see how it works. Delay 10 meters. Linearity 1, 30. That's interesting. No, not really interesting. So here we see this is like linear function. So the delay line is pretty short. That's why the bit node is very close to 0. So we have just to fix the window which is plotting here. And what happens that for just like regular lasers with 30 kilohertz and like any linearity, we can use just like regular DFBs for short range LiDAR with like 10 meters. We can use like any laser with any linearization. So linearization doesn't really help because your delay is pretty short. So basically what it means for short range LiDAR, we shouldn't care a lot about linearization. And what really helps is line width. But when we go from 30 kilohertz to 1 kilohertz LiDAR, the signal to noise ratio changes only by 3 dB, which isn't so important. And here, if we move to 1 kilometer, we're going to long range, very long range LiDAR. Nothing works. In reality, nothing works until you take extremely good linearization of your LiDAR. So basically, you for long range LiDAR, low noise isn't so useful because you see the bit node is like pretty broad, but linearization helps a lot. So it always improves your bit node signal. And for bad laser, 1 kilohertz, nothing can save your LiDAR system. It's working, yes, for you?
Yeah. What's your criterion to say, okay, I can work with this, for example, the middle figure? Is it possible to work with this? Is it a good guidance or?
So it should be one peak of your bit node, because in reality all the sliders should have a accuracy. Let's calculate. It should have its long range. It should be 10 centimeters, like 50 centimeters in hundreds of meters. So it should be 10 centimeter divided by, let's say, 1 kilometer. 1 centimeters. So this is 1 meter, and this is 1,000 meters. This is 1 kilometer. So basically, this goes to 10 to the -4. So your bit node, the bits of your bit nodes would be 10 to the -4 relative to this frequency.
Okay.
So this is definitely not the case of this thing. Because your system allows you to have this resolution, special resolution of, let's say, 10 centimeters, but just because of the bit node, you cannot use it. And another thing is signal to noise ratio. So basically, this is like ideal case. When we do this real-time signal processing, and this like 100 megahertz is already pretty high frequency for low-cost electronics, you will, with your just like windowing of your signal, will reduce the signal to noise ratio even lower. So it will be pretty broadband bit node. Reality you cannot use it. So it should be one sharp line, and signal to noise ratio in reality. So we have to replot it in the log scale. By the way, who want like additional task? you should replot it into the log scale, these things. Because in reality, it will change its view completely, and it will look like this. And what is good later, when here we have 30 dB of signal to noise ratio between the central line and the next sideband. And this is, of course, this chirp range in our case 10 kilohertz. Another thing, the important thing which we have to keep in mind is the sweep rate. If we will try to make it faster, it will move bit node to the to higher frequencies. Let's try. We do 100 kilohertz. Is it correct? Chirp frequency. 100. Grigory, is it right? We're moving. That's interesting. I have to check. It definitely should go to higher frequencies. We had it at 90, and right now it moved to 30. Let me think why. The frequency delay. Yeah, I think it's just some problems with the centering of this figure, because if we are going to 1 megahertz, it goes to the hundreds of megahertz range, and in reality we cannot detect it with regular electronics. So it should be like some really state-of-the-art things. But if we're talking about low-cost applications, for example, for automotive industry, this is just impossible to detect with like $10 electronics. And this guy, if we are, why it's not working at 100 kilohertz. I think just because of the centering, something is wrong with centering of this figure. No, nothing here. I expected to see something. Good question. I have to take a look at the code, what's going wrong here with this fast chirp. Usually we are not going so fast at these frequencies. In reality, I know what happens. This chirp is faster than our delay line. So basically, we are chirping faster than the light has time to come back. So we have our chirp local stator here, and it chirps faster when the light goes forth and back. So here we have to reduce delay line, and this is 190 here, and if we go to so basically when we are doing 10 kilohertz, the bit node is at 10 megahertz. If we are doing it much faster, 10 times faster, the bit node goes immediately to almost 100. That's how it should work. Yeah, and that's the thing which I promised you to ask you to take a look. So do you see this guy? This is on-chip spiral, which is used for linearization. And this is Silk targets robotic guidance with chip scale LiDAR. So that's in reality what they're using for linearization, this on-chip delay line for active linearization. And they have on-chip laser, which is low noise, and they're doing several kilometers ranging, which is pretty cool. Okay, I think it's also a spiral. We are almost done, Antonella. Yeah. Guys, do you need more time to take a look at this like Python script?
No. Answer, yeah, no. Okay, wait. You guys want to work more on this, or do we break now?
Break down.
Okay, we can break now. You just do here. Break here. We can break for those. Let's have a quick break. For those who have not yet recorded their pitch that we have to do, we can come back into the room in about 5 minutes. Actually, you know what? We're still going to have the same break time. We can use it also within the recording. Good with that? Okay. So let's break it. Have a big break. A minute. And everyone else can stay outside. And the 7 people that have to come back in.
Okay.
Good?
Yeah.
There, yeah. So,
Thank you.
now 11
Thank
o'clock,
you.
that should get something, right?
Mm-hmm.
Thank you, Andre. Thank you very much.
That's fine. Don't get me back. Okay, did you practice?
Я все выпустил. Не могу. Так, погоди. Надо было.